No. Hello, everyone. This is lecture 11 of PTRE 475-575. Unfortunately, we have a technical snafu, so the camera that is supposed to be showing me is not on, and I'm not able to. It's on, but it's not connected to the Zoom, and it doesn't give me that option in those cameras, so might be a little bit of a weird lecture today. Anyway, so we have a little bit of a short time game plan because the exam is set to be on March 3rd. And we have about 10 more slides to go through. And then we'll be ready. It will have all the material that is needed for the exam. My plan is if we finish the material today, and then we come back next week, the homework is due on the 26th. I should be able to go. I should be able to go over the homework either today or Tuesday, and then Thursday next week would be a review, and then Tuesday the battle, the exam. So I think it's a good timeline. The only thing is that the homework too may not be graded by the time the exam comes. Either way, I will give you the solution key. So bear in mind that homework 2 is due on Thursday. I cannot really go too much with an extension of that. I mean, I can, if there is people that really want an extension and they have a valid reason, I can extend like to maximum Saturday, but I really want to give out the solution key as early as possible. Now, homework 2, if you have seen it already, it's much easier than homework 1. It's more questions, but it's easier. And it's more straightforward. So it shouldn't be that much of a trouble. Please see it as easy points, okay? Easy points that you can get, and it can offset if something touch wood goes bad in the exam and you have a bad day, you can offset it with that. People started talking to me also about topics for the project, the term paper, which is nice. Please, as early as possible. The earlier, the better. Not as early as possible. The earlier, the better. We have time, but don't keep it until the very end. And also bear in mind that this is not the kind of term paper that you write a lot, and the more you write, the higher the grade becomes. You need to narrow down to a very specific hypothesis, and that should be easily testable. Okay, so last time we got to slide 9. We looked at tubular routine pipe calculations. We talk about near wellbore tortuosity and what this causes, why this is bad. It causes early screen outs and poor stimulated well productivity. We saw the results of a tracer test that showed fluid from one stage appearing to another stage. This is a pretty famous figure, actually. And we talk about the basics of modern day completions. And before that, it was an overview of the things that control your decisions on the completion design. And then we saw some typical configurations that you may find applicable. Different versions of those, of course, do exist, but these are the main ones, the primary ones. Okay, so we are stuck on slide 9, which was an example problem that was a little bit long, so I was like, I couldn't finish it last time, so I didn't start it. Let me put my phone on silent. Example problem number 1. A 2,250 feet long intermediate casing of 9 5/8 inch outer diameter OD by 8 and 3/8 inch inner diameter, weighs 32.94 pound mass per foot, is followed by a 7,750 feet production liner of 7 and 5/8 inch outer diameter and 6 and 7/8 inch inner diameter in a well section that was drilled with an 8-inch bit. Calculate the total inner volume capacity of the well and its total angular capacity. The production ratio, the production liner, excuse me, is not cemented and no packers have been set. So this sounds like a very long and complicated problem, but it's actually quite simple. One second. I think I know what is the issue with that. Let me, uh, let me turn on. Try to. This is gonna turn on the camera, but it's not really. Anyway, so we have an information for our wellbore architecture so far. It is pretty simple. We have a well. Let me get the marker. We have what we call a 9 and 5/8 outer diameter and something like a 8 and 3/8 inner diameter. Which is something like 2,250 feet long. And we are given its how much it weighs, etc., etc., 32.94 pound mass per foot. And then beneath that, we have 7,740 feet of production liner that is like 7.5. So basically, inside that is 7 and 5/8 inch outer diameter, 6 and 7/8 inner diameter, and 8-inch bit. It tells you once we set this first intermediate casing, we went with a 8-inch bit and we drilled a hole that was basically 8 inches. Inside it, we ran a, let me make it orange or pink. No, let me make it orange. It's gonna do a good contrast with the purple. Inside it, we have a production liner, 7 and 5/8 inch outer diameter, and 6 and 7/8 inch inner diameter. Now, calculate the total inner volume capacity and the total angular capacity. And then it gives you a hint in parentheses. The production liner is not cemented and no packers have been set. So it's lying there. Let me make it. So this is how it goes. It's latching onto the where the intermediate casing ends. The fact that it's a liner is actually sort of like a keyword, but I'm making sure I have the parenthesis so that you can see, you can make sure I. Oh, there you go. Okay. So I'm asking you, how much fluid can I fill into this system and also the annulus? And let's see first the inside, the inner, total inner volume capacity. I will remember this picture because it might, I need to take it out. So delete. Okay. So the inside of the pipe, I'm talking about the intermediate casing. We know it's 8 and 3/8. This translates to 8.375 inch. So if we do that, 8.375 square divided by 1029.4, which is what we dwelt on last lecture, that very important conversion factor that I kind of want you to remember by heart. It gives me something like 0.06814 barrels per foot. So every feet of that intermediate casing carries 0.06814 barrels every feet. And there is what? 2,250 feet of that. So I multiply that, well, I'm going to do that later. Beneath that, we have the liner that the inside diameter is 6 7/8. That is 6.875. So I do that 6.875 square divided by 1029.4. I get something like 0.04592 barrels per foot. This is a little bit smaller than above, which makes sense. It's a smaller pipe, right? I can feel less fluid in it. Now, okay, now if I go backwards, will I show me my drawing? No, okay. Now, to do the volume of the fluid inside the pipe, I just need to multiply by the length of each section. So I take the first number, 0.0816814 barrels per foot, times 2,250 foot of those. Feet cancel out, and I only have barrels. Plus 0.04592 barrels per foot times 7,750 feet. You add those together and you get something like 509.2 barrels, which is a logical value. I need 509 barrels to go 10,000 feet deep. It's a logical estimation. Now, how do you call it? This is the inside of the pipe, okay? The inner pipe capacity. What about our inner pipe volume? What about the annulus side, which if you remember very well, we now need to use, let's go this equation, the second one, this. So we need outer diameter and inner diameter of the fluid flow part. So now what is going to happen is that we have the trick there. The intermediate casing has been cemented, so there is no annulus there, okay? It's only zero, it's 0 barrels per feet, okay? No casing. And underneath it, I want to draw again very quickly this picture because I left space when I was drawing it to make, it was something like it was with purple going down. And then I had 8 inch, and inside the 8-inch, it was a liner. Oops. Sorry for the very, very bad drawing, but I tried to emphasize the annulus there. There is annulus at the bottom, so the fluid can go here. Between the liner and the hole, but it cannot go above that. Okay, above the intermediate casing is being cemented. So the weird scenario, I agree, but the situation now is something like that. It looks like this. This is the hole made by the bit. It's 8 inches wide. The hole is as wide as the bit, right? And then inside, I have the outer diameter of the liner and the inner diameter of the liner. The liner is solid. It's metallic. Now, between that, I have this pink fluid that I'm trying to measure how much I can have. So now my outer diameter is actually of the fluid flow conduit is the bit diameter. That's why I have 8 squared. And then the inner diameter is actually the outer diameter of the liner, which is, what is it, 7.625, which is 7 6/8, something like that. I forget what was it. Yeah, 6 7/8. Sorry. Okay, it gives me something like 0.0569 barrels per foot, which is tiny capacity. Capacity is barrels per foot. So I need to multiply by its length, which is something like 7,750, and I get 44.12 barrels, which is like tiny, tiny area there. So this well is a little bit weird. It's a temporary architecture, but well, you can find this actually in real life as well. So you need 509 barrels to go down the well, and then 44. You can only go by 44 barrels up, and obviously you cannot circulate out through the annulus because the intermediate annulus is cemented. Yeah. Any questions on this problem? It's easy but important. And you know, real life can be way more complicated, you know, but it's gonna be, you're gonna be applying the same principles actually. Okay, if there is no questions, I will move on to the next subtopic, which we are gonna see some equipment that you may find in the website and what are they used for. And these are equipment related to well completions. If you go to our drilling and completions laboratory, which is basically a warehouse that the university has leased or the college has leased for like 10 years, it's called, Drilling and Completions Laboratory. We have some samples of this kind of equipment. And yeah, they all have a function. So casing scrappers and junk basket. Some of them, their name is self-explanatory, some others not so much. If you have any questions, please let me know. I mean, it's fairly easy. It's like casing scrapper cleans up the inside of the casing. So a downhole tool incorporating a blade assembly that is used to remove scale and debris from the internal surface of a casing string is generally run on tubing or drill pipe. Casing scrapers or scrapers are routinely used during workover operations to ensure that the wellbore is clean before reinstalling the completion string. So workover operations is when you go to a well which is currently under production and you are trying to do something to fix that well. Okay, you have a small rig that will help you pull out any temporary components of the well bore architecture. And if you, when you are running it back in, you may want to run a casing scrapper to clean up, or even when you are running it out, so that you clean up the inside of the casing from any debris, etc. You can still get stuck during the process. So with the casing scrapper, you help prevent that from doing so. It's not as likely that you're gonna get stuck during workover operations, just as much as you have that in drilling. In drilling is the most common operational problem, getting stuck. But in workovers, it's not impossible. And but workover jobs have been quite, they are not uncommon. They are not uncommon. There is several companies that are dedicated to this task, workovers. And it's not a bad job to have, actually. The workover rigs are smaller. They're generally not portable. They are trailer mounted. They come with their own vehicle, basically. And you lift off the mast, which is like almost like a small derrick, and you go down the hole, you cut the production from that well, you shut it off, you go there, intervene, fix what you need to fix, change what you need to change, add what you need to add, then pull out of the hole, get it back online, and then you leave. You go back to the facility. Junk basket or SAP, that's exactly what its name says, cleans up dirt, a downhole tool with a profiled external surface designed to catch and retrieve junk or debris from the wellbore. The debris is carried up the tool string annulus in the circulation fluid, an indented profile creating a larger annular area causes the fluid flow rate to drop and allows debris to drop into the basket or receptacle located at the base of the tool. I have seen metallic junk basket like this one in this picture, but I have also seen cloth one made by cloth, which is like thin fabric. Is to remove any debris from the well and basically uses it uses like I don't want to say it's not complicated hydrodynamics, but the way it's moving is basically helping the dirt get into it. And when you pull it out of the hole, you pull the dirt with it, and then you remove the dirt basically from the well. Then that can cause you a million kinds of troubles. I mean, it can disturb your electric submersible pump. It can, we're going to talk about those later in a bit further motion. They can cause a lot of problems. It might be a good idea not to have a lot of dirt in your well. Also, dirt accumulates. We talked last time about fines migration, sand coming into your well, maybe because the sands you are producing from are very loosely consolidated, or because you are pumping too fast and too hard that makes the sand come into your hole, or a combination of both. So you may be able to get a lot of sand out of the well. If a lot of sand has accumulated inside the well, you may be able to get it out with a jack basket or some other standard downhole. Next, tractors. Okay. We have seen earlier in this module how modern day completions look like. And like one word to describe them is long laterals. Long horizontal laterals. The horizontal wells have very, very long laterals. They go miles. Okay, they go miles. There is a lady from Colorado. Her name is Trisha Curtis. She used to consult on Pentagon projects. And we tried to get her over to give us a speech, but it's a little bit hard to do that. We might at some point, but she has a very nice plot in her slides, which shows that even though rig count has dropped since COVID, and people are saying, okay, there is less drilling going on, there is less, you would expect to be less production. But the laterals have gone longer and longer and longer. So we're becoming more efficient in terms of productivity from one well. We produce more oil from one well than before, which is very nice. Very nice. Now, long laterals, they have this problem compared to vertical sections. The vertical section, you have gravity that can help you move things. So if I'm trying to get something down the hole, I can use gravity to help. Once I get to the lateral, it's the kickoff point, the landing point, and then I'm horizontal. So gravity won't do much, okay? Won't do much. So how do I move things along these very miles-long laterals? It's actually a very important challenge. And the answer is with electric over hydraulic power relationship. When you see a picture of that, you will understand how it works. Overall control, communication, and power are electric, but the parts and functions are performed hydraulically. Provides driving force at the end of the wire using traction wheels and that are deployed out as the unit is powered. Each wheel uses its own independent hydraulic motor for rotation. So it's basically like a little device with wheels that can move along the lateral. And it can help you transport stuff along those great distances. I mean, miles, where gravity cannot help you. Speed and force dictated by the number of drive sections. Utility examples where you can use it: scale milling, brushing and polishing, debris removal, logging while tractoring. We have that for the horizontal sections. Valve manipulation, plug pulling and setting, perforating, if unable to pump guns down hole. We're going to talk about perforations later on in this module in more detail, but the way it is over, this is how it looks like. You see the little wheels. I think from the picture you can understand how it works. Helps you move stuff along the lateral. This is how it looks like from nearby. And of course, like I said many times, research and development is taking place as we speak. So these kind of equipment are constantly being improved and made more adaptable to the downhole environments they are supposed to operate. And they look, they are constantly being developed. I mean, they are human interventions. They assist human intervention downhole. Now, parachute for pumping downhole is very similar. And I would, once you see the picture again, you will understand how it works. So a few words about it. It's a pump down sub, as we call it. It helps you pump downhole. It expands and contracts with changing internal diameter of a wellbore, giving you centralization and a large surface to pump against. Popular in operations requiring horizontal deployment of a tool string. It has a through contact rod, so you can pump down anything from logging tools to perforating guns. Can be run over wireline with an Acme thread or below the cable head. Reduces the amount of fluid and horsepower required for moving your tool string through the lateral section of a well. Sometimes there is laterals that king a little bit upwards, and in that case, you actually have to work against gravity. So not only gravity is not with you, it's actually against. And this is how it looks. So I think you understand how it works. You pump in one direction, and it basically blows open, provides more surface area you can push against. Now, if you try to go the other way, you will just close it, and then you basically lowers the surface area and you are pulling away, basically, when you are pulling out of the hole. So this is how it works. There is no like crazy, it's very, very smart design, but I'm gonna say there was no like crazy amount of science behind those. I mean, I think it's pretty self-understandable from the, or like from the pictures, you understand how these are, what are their purpose and how they work, more or less. Very important pieces of equipment, don't get me wrong. And some very smart people design those. And I hope some of you are going to get jobs into service companies designing this kind of smart equipment. Any questions on those? Okay. So, fishing is again a very, very common term in the oil field. If we're gonna go fishing, doesn't mean we're gonna go catch fish. Well, we're gonna catch fish, but a different kind of fish. Fish is anything left in the hole, either intentionally or by accident. And you want somebody to go there, fish it out of the hole. Okay, it's called fishing. We can use wireline for fishing operations. Most service companies, they have their own fishing sort of part of the company. It can be drill pipe, tubular, wireline, tool strings, from broken cable, among others. I was in a rig in August, was it August or maybe September or October of 2021. And it was a very sad story that we got stuck. We fought it for like 10 days. Couldn't do anything about that. Eventually gave up, had to cut the very expensive BHA that had a $1 million logging while drilling tool. And then we had to bring a company to fish out of the hole everything that they could fish and cement what we left behind and sidetrack around it. And the tool wasn't even insured. So it would have been like 750,000 or something if it was insured, but it was like almost $1 million, like 900,000 or something. Anyway, by the way, this was supposed to be an easy well. I don't want to give specifics, but in every report, you have the amount of money spent on that well so far. It was like a little bit over $1 million. It wasn't that expensive. And suddenly you have a loss of about that, doubles the cost. That's like not normal, or it shouldn't be normal. It's normal for some companies, I guess. But anyway, fish may also be anything that you leave downhole intentionally. So it's like I said earlier, is intentional fishing like something that you left downhole on purpose and you are planning to get it, or like something you left unintentionally? In our case, it was problem induced, I guess. Wireline operations now use quick release tools with the utilization of greaseless wireline. This is necessary since there is no rope socket and is able to withstand much higher tensions. Let's see. In preparations for the event that anything is left downhole, it's imperative to know the dimensions of the equipment. Okay. Okay. What I was trying to say with my own story is that we brought a company to cut above where we are stuck. Where you are stuck, you are calling it, it's ironic, the point that at which you are stuck is called the free point. Okay? Or think about it, the point that you want to free. You want to go and cut right above that and remove whatever you can out of the well. It's not exactly fishing, but we had to bring a separate crew. Generally, the fishing crew, it comes with the equipment comes with its expert from the company. You are signing a contract with the service company that will do that for you, do the job, that specific job for you. So you want to know the dimensions of the equipment. If you cut the downhole, if you cut the drill string, and you really don't know how the part that you cut that is staying downhole that you want to fish, how does it look like? It may not look like the way you expect it to look like, and the way it looks like is important because it's gonna help the expert that comes with the equipment, or the expert in Houston or Denver, most likely Houston, decide what kind of tool is best for you to use. Remember, this is an expert. He's gonna work with the operator, and it's good that he has as much information as possible. Many times, you will see that the BAJ is going downhole, and well, sometimes, not many times, and they don't really know its design very well, or they are not very certain about its design and what is there. You need to know what is going downhole. You need to have it in plan so that if you cut or anything that happens when the bead is touching the bottom, etc., you will be able to know. Because remember, the earth is opaque; you cannot see. Profiles, outer diameters, length. I want all this information. This is gonna help the expert decide. The expert is doing this job full time. So he goes from one fishing job to another. So if you show him, if you give him the more information, the more relevant information you give him, the better. So you want all the information that you can possibly have, relevant information. Don't tell him what you like for food, for instance. Having this knowledge allows for the design of fishing operations and retrieval. For example, If a wireline tool string is left downhole, knowing the outer diameter of the top or most likely section to be grabbed, the one that you want to grab, allows for correct selection of the appropriate fishing hook, such as an overshot. We are going to see several fishing hooks soon. Knowing the length of the tool string allows for the proper length of lubricator for retrieval. Now, this may sound weird, but it's going to become clearer in the next slide, which shows here the fishing configuration on top of the blowout preventers. This is fishing done during drilling operations. So you have this little structure here that goes, let me use the wireline drum, sheave, goes up, another sheave. And then you have the stuffing box. Something goes inside the, basically, that's where the part that you don't see starts. And you don't want the stuffing box to leak. It can leak. It can be leak. It can leak because it's faulty. It can also leak because it's not, doesn't have the specific pressure rating that you are asking it for. So that's where basically the wire line goes downhole, starts going downhole. And then you have this little lubricator, wireline rams, BOPs, and then you are down the well, down there for real. But you are really downhole from the stuffing box. The thing is that when you retrieve that fish, you are gonna close the rams, and then you are gonna close these wireline rams when you retrieve the fish. The fish will be here. And you will try to open the lubricator and take it out. Okay, so you want the fish from this all the way up. You're gonna open the lubricator, get it out from there. The lubricator length must be big enough so that you can actually retrieve the fish, because you need to close the wireline rams. Okay, so the length of the lubricator that you're gonna use has to deal with the length of the fish that you're gonna try to retrieve. So that's important. Not knowing the dimension of tools can lead to operational failures as well as safety issues. For example, if the length of the fish is not known and the fish is retrieved and brought to the surface, insufficient lubricator length may prevent hydraulic BOP valves or wellhead valves from closing properly. So it's what I was describing earlier. Many times you don't really know, you may know the length, but you may not know the profile because you cut it as it was downhole. So you really don't know what it looks like. You have an idea, but you really don't know. In this case, you do what doctors do to a patient, which is like X-ray kind of, but even easier. Well, even more simple. You stop the part that you broke with something called impression block. This is going to leave an impression of what it broke, of what it hit on the impression block. It's like a mold, like the dentist does a mold of the teeth, and does whatever, I guess, we need to find out something. It's the same thing that what you are doing now. You are stopping the fish with an impression block to understand what is looking up, as we say, okay? An impression block is put on end of tool string and run in hole. So you go down hole with the impression block and you intentionally apply pressure on the on whatever is facing up. So and then when you retrieve the impression block, you understand from the impression block, the impression of the impression block, what is looking up, how it looks like. The fish is then hit hard to leave an impression on the soft end. The black end is soft, giving an estimate of the dimensions of the fish. Therefore, we can imagine how important it is to have estimates of what tools are being run in whole in the event that anything is left down whole. Also used for anything other than tool string to diagnose an issue like casing failures, etc., etc. There is similar impression blocks, not like this one, but you can actually, I want to say scan, I want to say scan. You basically survey the side of the casing at specific depths to understand if you have casing failure, like by corrosion or mechanical means or thermal means even, and understand what is needed at that point. So all this is because of one reason. We cannot see what is happening down home. It's dark down there. I don't want to say it's cold. It's dark, you can see. It's dark and scary. Fishing tools. So what I mentioned earlier, you have a lot of equipment at your disposal. And the reason is that there is different, like infinite kinds of fish you may need to retrieve from the well. There are some tools that work best for one kind and other tools that work best for another kind. And we're going to see some of those. This is not all the types of fishing tools that exist. For instance, hook or claws. It goes inside the fish and grabs onto it from the inside, pulling it out. So imagine if the fish is like, if I can. Something like that, an opening like that. These little fins attach onto the inside and with friction help bring it upwards. When you are fishing out of the hole, many times you need to fish very slowly. You need to pull out of the hole very slowly so it doesn't fall. The fish doesn't fall. I have heard stories, people going as slowly as 1 foot per 1 foot per minute or something, like very, very slowly to get it out, even less. But that's how the claws work. You grab from the inside. Spear, similar, very, very similar. Now this one is a taper tab. It is like a screw. The more you screw in, the bigger the diameter it becomes. So you are gonna be rotating that, and you are gonna be screwing it into the fish. Sorry. Taper tab. Well, if you 1 second, where is the mouse? Okay. Here, the more you screw, it goes deeper in the fish. The diameter becomes bigger and bigger, and eventually it's gonna get attached, and then you're gonna pull out. It's good, especially if you don't really know what kind of dimensions you have of the fish pad. So it's pretty practical. Taper tab is pretty common, actually. Fishing magnet, I don't need to explain how that works. We have one in Racola, if I'm not mistaken. So if I'm there in the tour, I will show you. Reverse joint is the opposite of a taper tab. The diameter gets smaller as you drill through, and the difference is that the reverse joint is basically gonna sorry, this is the, I don't know if it's a reverse join or dicollar. They are very similar, but ultimately, oops, sorry. Ultimately, what they're gonna do is that you have the, sorry. You have the tubular, again, where is the mouse? Okay. Oh my God. Okay, so now I'm here. This is what I'm trying to retrieve. I'm screwing on it from the outside, okay? And the diameter becomes smaller and smaller. I want to start with a big diameter and get smaller and smaller until it gets attached. And you don't want permanent attaching, but you want it strong enough to bring it out of the hole, obviously. So these are some fishing tools that are of use in the industry. Another one, if you hear, there is two big categories of fishing tools. If you are trying to grab the fish from the inside, it belongs to the spear category. And I know we have seen spear is one thing, but basically it's used interchangeably with a big category of fish that you grab from the inside and overshot from the outside, okay? And like the dicollar is an overshot, kind of. Okay. And this is a point where hackers, that's where the exam one is gonna be up to this slide, which I believe is slide 20. Yeah, slide 20. This is gonna be the material that you're gonna be tested on March 3rd. Everything that we did up to this point. Packers, etc., would be later for the second exam. Yeah, those will come later. Since we have 15 minutes, we have more than 15 minutes. I think rather than getting into packers, I will first ask if there is any question on the fishing tools. If there isn't, I can go over the homework very quickly. And, okay. So homework two. I made a mistake. For a little while, the homework wasn't visible to some of the students. It turned out it was my mistake. I was playing with the viewing settings and I pressed something I shouldn't press and I didn't notice it. So, homework two. First of all, homework one is due tonight. I extended the deadline. Your TA is arriving, is in Houston for a conference. He's coming back on February 20, sorry. He's coming back this Friday, maybe around 2. So after that, he's gonna try to start grading homework one. And then, but you will have the solution key earlier. And then you guys have homework two on the 26th. And the same day, we are gonna do a review of for the first exam. Last year, I used two shorter lectures for review, but it was like a 50-minute class. This year, I'm gonna use like one big lecture, so 75 minutes. But I am available if you have any questions. Also, if push comes to shove and we are behind where we need to be with the preparation for the exam in the on Monday, I can also have a session. But yeah, I mean, we are gonna see. So, homework number 2. Due Thursday, February 26. Question number 1. What is the failure mechanism, tensile or shear compressive failure in borehole breakouts or washouts? We talked about those. They always happen in the same direction, in the direction of the least compressive principal stress acting on the hole. So for vertical sections, it's going to be always in the direction of the safety in. There is a reason for that. So is it shear failure or tensile failure? Then hydraulic fractures induced for stimulation purposes. Are they shear failure or tensile failure? Or actually, it's shear compressive or tensile? The question is because there is other kinds of shear failure. There you can induce shear not by compression. Part C, fractures induced during drilling that leave an imprint on image logs, like you saw on homework 1. And I say in parentheses, along with borehole breakouts. So those fractures, they are not the same as the borehole breakouts, but I'm asking, you see them on the image logs with borehole breakouts. So are those failures, the drilling induced failures, are they tensile or shear? And then part D, slippage along pre-existing faults inducing seismicity triggered from wastewater or saltwater injection in wells near hydraulic fracture sites. Are those tensile or shear compressive failures? I don't think there is any question on the question number 1, but if there is, please let me know. Using your petroleum engineering background and your hopefully evolving knowledge on completions, which of the generic well completion methods shown on slide 2 of module 2 will suit best? So I want you to go to module 2, slide 2. We spent some time on this slide. So take this slide and answer this question. Which one will suit best? A well targeting 2 separate zones located at different depth intervals? A well targeting a zone with a very sour, containing highly corrosive H2S quantities of natural gas? So the natural gas produced from that well is going to be very corrosive. So what kind of completions will you propose as a completions engineer for the design of that well? A well targeting a region of loose unconsolidated sand with dangers of fines migration but good permeability? Okay, we said fines migration is something bad for my well. I want to keep it away. So what will I do? What kind of completion I will propose for that well? A well targeting a region of loose unconsolidated sand with dangers of fine migration, but with bad permeability, okay? So part C, I forgot to read it. It has good permeability, okay? Part D has bad permeability. Okay, how do I deal with that? Okay, what do I do to deal with low permeability? There is something I can do for that. Any questions on question number 2? Okay. Calculate, question number 3. Calculate the capacity in barrels per foot for the annulus between a casing of outer diameter of the 9 and 5/8 inch and inner diameter ID 8.755 inch and a tubing of 4.5 inch outer diameter and 4 inch inner diameter. So what is the capacity for the annulus? That's very important. Basically, I'm giving you I have, oops, sorry. Casing, outer diameter, what is it? 9 and 5/8 inch. Inner diameter, it's 8.75. Notice I'm giving you those answers, those inputs in different ways so that you become used to it. Like, obviously, I think you can convert 9 and 5/8 to a fraction, right? Very easily. So, and then inside I have a tubing that has, let's use purple for the tubing. Outer diameter is 4.5, inner diameter is 4. So now the question is, I want to fill it with, well, it was a pink fluid that we, sorry, I lost the mouse again. It's on the other screen. Let me get it. I want to fill this space. So my outer diameter is really the inner diameter of the casing of the fluid flow, the outer diameter. So it's like something like 8.755. And the inner diameter is actually the outer diameter of the tube. So don't get confused with that. It might say inner diameter, but I might be looking for an outer diameter value. So it's an easy question. And I want the capacity in barrels per feet. You have the equation that you need to use. It's very easy. So far, the whole homework is a gift, it's like a very, very easy question. Question number 4. What is the purpose of the following oil field tools and equipment? Tractors and impression plugs. We just talked about those a few minutes ago. So use a small paragraph to describe each. Very, very small. Not a lot of, like 5 sentences. 3 to 5 sentences would do. Maybe 4 to 6, I don't know. Depends. Don't go too much, don't go too little. Question number 5. What is the total volume capacity? Now, volume of the wellbore displayed in the schematic below if the well's measured depth is 21,313 feet. So look at this well below. It's 7 inch. It has casing that is 7 inch inner 7 inch diameter, 7 inch outer diameter, excuse me. And then next to it, 40 pound is like 40 pounds per 40 pound mass per feet. And the inner diameter is 5.836. Okay. So and then I have a liner that starts from 10,050 feet all the way down to, what is it, 21,313 feet. And the inside, the liner is 5 inch outer diameter, 4.408 inch inner diameter. So I want to calculate the volume capacity of the well bore. So imagine this here. I want to get the marker. It's filled with some kind of fluid. And I want to figure it out. What kind of fluid is this? And how much fluid in barrels? Remember, it's volume now that I'm looking for, not capacity. So in question number 3, I was looking for capacity. Here I'm looking for volume. So I'm gonna go from capacity times length to volume. Don't get confused. It's very easy problem here. Very easy. Any questions? Okay. So last problem is consider the wellbore displayed in the schematic below. I have a little horizontal well, I guess, and I have some kind of it's a casing that goes, a production casing that goes all the way from the surface. It's kind of rare. See this especially for this kind of long well, but it's not impossible. Calculate the flash volume if the well is 23,471 feet long. So I'm giving you enough information to calculate the flash volume. 1 second. Let me just make sure I want to check from my phone the solution key, so I'm not making a mistake here with what advice I'm gonna give you. So here there is a catch, a small catch. Okay, and then yeah. So I mean, if you see the schematic of the well, it's more simple than what you expect. So I want to flash volume. I want to get, sometimes it's used in the field, like I want to flash to that depth, but I'm telling you here, I want you to flash until the very end of the well. So basically, pump fluid up to the end, up to this point here. So 23,471. I just want you to tell me this volume. How do I know on the surface that I'm added to that volume? On the surface, I'm counting how much I'm pumping, how many barrels I have pumped. Then I want to know basically, how do I know I made it? Part B, you want to spot acid and let it soak on perforations before starting the frag operation. This will be done using a frag spread as wireline this will be done using the frag spread as wireline is currently down doing a rehead and are not able to run in whole. How many barrels will need to be pumped from the surface? You want to spot acid at 19,500 feet. And that's actually very similar to the question above. You don't want to go all the way down. You don't want to make it all the way here. You want to make it somewhere here. So I just want this one. It's quite simple, actually. Very, very simple. Very, very easy homework. Yeah, nothing really crazy. And I think, yeah, it's how long would it take me? Like an hour and a half or something. It should be very easy. But most importantly, don't leave those points behind. These are easy points. Okay. get those points, maximize, so that if things become a little bit hard in later homeworks or in the exam, or maybe in the term paper, you don't get the grade that you would like to get, to have this. You are not going to be saying, oh, I wish I had done better on that homework. Anyway, so this would be the homework 2. And yeah, it's due next Thursday. Well, since we have, I guess, a couple of minutes left, is there any question on homework 1 that is due tonight?
Not at the moment.
Okay. Okay, Sarah. Okay, then I guess no question, I guess, yet for homework 2. We'll call it a day. So thank you very much. Have a nice weekend. We'll be available by email if you need me and the TA. So yeah, if you have any questions, please let us know. And yeah, I will see you on Tuesday. Thank you very much. Have a nice rest of your day.
Likewise. Bye-bye.
Bye. Thank you, Donald.
Thank you.